The world around us is composed of innumerable particles, from the air we breathe to the cells constituting our bodies. But what makes up these particles, and how do they interact with each other? The cells in our bodies work in harmony, forming tissues, organs, and ultimately constituting a complete organism. Zooming in, we discover that each cell is composed of countless particles, including protons, nutrients, and electrons. Going even closer, we find quarks, which make up these particles. The entire universe is a vast assembly of quarks and other subatomic particles interacting through the fundamental forces of nature. The universe emerged from the scorching heat of the Big Bang, undergoing continuous expansion and evolution. Despite the chaos and destruction throughout the process, the fundamental laws of nature remained constant, providing a stable foundation for the emergence and evolution of life. Gazing at the stars, we are awestruck by the perfection of the universe, from the countless galaxies and stars scattered across the sky to the intricately woven systems governing the behavior of the cosmos. Everything seems meticulously designed, and this perfection is reflected in the delicate balance of the physical constants that support the birth of life. In the chilling expanse of the universe, the conditions for the emergence of life are incredibly stringent. It requires precise coordination of all the physical constants in the rules of the universe, from the speed of light to the proportions of the four fundamental forces, to support the birth of life as we know it. If any of these constants were even slightly different, the universe would be unable to sustain complex chemical reactions and biological processes, and life as we know it would not exist. This precision and ingenuity leave one wondering why the universe is so perfectly tuned. Around 380 BCE, the astronomer Eudoxus created the first theory of celestial motion, introducing the geocentric model, which dominated human understanding for about 1,400 years. During this period, humans believed that the Earth was the center of the universe, and the Sun, Moon, planets, and stars all orbited around the Earth. This was known as the geocentric model. As observations progressed, issues with this theory became apparent. Astronomers observed planets, at times, seeming to move backward in the sky, a phenomenon known as retrograde motion. To explain these discrepancies within the geocentric model, astronomers had to introduce increasingly complex systems. In the 16th century, Copernicus proposed a revolutionary cosmological model. His heliocentric model placed the Sun at the center of the solar system, with the Earth and other planets orbiting around it. Copernicus's ideas contradicted the authoritative views of the Catholic Church, challenging human beliefs and facing suppression for a long time. However, with support from observations by figures like Galileo, the heliocentric model gradually became the mainstream perspective in the scientific community. The significant technological advancements of the 20th century and the improvement in our ability to study the universe have allowed astronomers to observe the cosmos with increasingly large telescopes. This has provided us with a clear view that the Sun is just one of billions of stars in the Milky Way galaxy, and the Milky Way itself is just one of potentially tens of thousands of galaxies in the observable universe. Our understanding of the vast and deep universe did not stop there. With the work of scientists like Edwin Hubble, we learned that the universe is not only vast but also expanding continuously. This led to the development of the Big Bang theory, which posits that the universe originated from a colossal explosion around 13.8 billion years ago. All these discoveries raise a fundamental question: are we unique in the universe? The answer seems elusive. On the one hand, we are just a commonplace entity in the ever-expanding and infinite universe. On the other hand, the conditions that allow for life to exist on Earth are very special and rare. From the tilt of the Earth's axis to the precise position of the Moon, the Earth's environment happens to be perfectly suitable for the existence of life as we know it. At times, we can only make the most basic assumption that, regardless of how the universe operates, it does so in a way that allows for the emergence of intelligent observers like us. This line of thinking is known as the anthropic principle, proposed by physicist Brandon Carter in 1973 on the 500th anniversary of Copernicus's birth. He suggested that, while our position is not necessarily at the center of the universe, we enjoy a certain privilege to the extent that our existence as observers is possible. The weak anthropic principle in this theory essentially states that we cannot find ourselves in any other universe that would prevent our existence. Therefore, our universe must be the way it is. The strong anthropic principle goes further, suggesting that the universe must have the qualities necessary to allow intelligent life to develop at some point in its history. However, these interpretations of the anthropic principle do not consider that probabilities are not absolute but are based on a specific set of conditions. Once all conditions are established, the occurrence of an event may become inevitable. Thus, the existence of life does not necessarily imply the perfection of the universe. Furthermore, relying solely on the anthropic principle to explain the perfection of the universe overlooks the fundamental goal of science, understanding the natural processes of the universe. In the early Middle Ages, philosophers and scholars began exploring the essence of the universe and the origins of life. In the 13th century, Bradwardine Seguier wrote The Eternity of the World. Seguier, during his studies in Paris, the intellectual center of the time, participated in the radical Aristotelian movement. This movement sought to integrate the views of ancient Greek philosophers with Christian doctrine, asserting that philosophy could complement and deepen religious beliefs. Influenced deeply by these thinkers, Seguier's philosophy emphasized the importance of reason and the power of human wisdom. He believed that philosophy was a necessary supplement to theology, and the truths of faith could be elucidated and understood through logic and argumentation. Seguier challenged the traditional view that the universe has a definite beginning and was created. Instead, he proposed that the universe has always existed, being eternal and self-sufficient. According to him, there is no clear starting point for the physical universe, and there is no definitive first human or specimen of any particular species. His thesis sparked intense debates among scholars and theologians of the time. Many considered Seguier's ideas to be heretical, posing a threat to the foundations of Christian faith. But others saw an opportunity for a deeper and richer understanding of the world. Seguier's concept of an eternal universe found a resurgence in the 20th century with the development of the steady-state model. In the steady-state model, the universe is considered perfect as it continuously maintains a state of balance and symmetry. New matter is constantly created to replace the material lost as the universe expands. This theory was proposed by Hermann Bondi, Thomas Gold, and Fred Hoyle in 1948, based on what is now known as the perfect cosmological principle. The perfect cosmological principle assumes that the universe is not only spatially uniform but also uniform over time. According to this theory, the universe has always been in a state of perfect balance, with just the right amount of matter and energy to sustain its expansion. This seemed to provide an explanation for why the universe appears so perfect. Although the theory received acclaim, even garnering the favor of Einstein, issues with the steady-state model began to surface in the 1950s and 60s. Astronomers discovered radio galaxies and quasars, observable only under conditions of accelerated cosmic expansion and high redshift, which contradicted the assumptions of the steady-state model. However, what ultimately overturned the steady-state model was the discovery of cosmic microwave background radiation in 1965. Faint background radiation fills the entire space uniformly in all directions. This discovery paved the way for the Big Bang theory, considered the best explanation for the origin of the universe. According to the Big Bang theory, the universe expanded from a hot, infinitely small singularity, and the background radiation is a remnant from the intensely hot early period of the universe. The steady-state model, which preceded this theory, failed to account for the origin of this radiation. The idea of the universe originating from a single point was initially proposed by the Belgian cosmologist and Catholic priest Georges Lemaitre in a 1931 paper on the primordial atom theory. In an earlier paper in 1927, he had derived from Einstein's equations the conclusion that the universe was expanding, and the velocities of galaxies were proportional to their distances. In 1929, Edwin Hubble provided more detailed data confirming the relationship between the distances and velocities of galaxies being proportional. In 1964, George Gamow proposed the idea of the universe expanding and cooling from an initial state of infinite density in temperature. He also suggested that all protons, neutrons, and electrons existed in a sea of high-energy radiation. His calculations explained the relative abundance of hydrogen and helium but did not account for heavier elements. This raised a crucial question: have the laws of nature remained unchanged since the Big Bang 13.8 billion years ago? In the 4th century AD, Aristotle believed that one of the primary goals of physics was to study change. If the known physical rules changed over time, the search would be for the cause of such change and the discovery of a physical law. The ultimate aim was to formulate a physical theory independent of time. Any variation in the fundamental forces in the universe would have catastrophic consequences. In our universe, there are gravitational, electromagnetic, strong nuclear, and weak nuclear forces. If any of these forces were to change, one can imagine the universe becoming highly unstable. If gravity were not constant, reliable predictions about the motion of objects on Earth, the orbits of celestial bodies in the solar system, the flight paths of aircraft and spacecraft, and physical phenomena such as gravitational lensing and cosmic expansion would be nearly impossible. If the electromagnetic force is not constant, the binding properties of electrons between different atoms would become highly uncertain. Every molecule in the universe could potentially change its properties at any moment. If such a scenario were to happen to humans, we would immediately fall into an unsustainable state. If the strong and weak nuclear forces were to change, it would bring about rapid and catastrophic disasters. We wouldn't even have time to comprehend what is happening. Unstable atomic nuclei would spontaneously decay into more stable structures, releasing tremendous energy in the process. Atoms would lose electrons, forming a plasma universe, the consequences of which are so complex that we cannot fully understand the scale of the destruction it would cause. But if we were to fine-tune other parameters of our universe, could there exist a stable universe with different physical constants and natural laws? Schrödinger, with his brilliant equation, showed us the concept of superposition, where all possible outcomes of a quantum measurement exist simultaneously in some universe. The universe we observe is just a drop in the ocean of possibilities. In places we cannot see, there is more space, more stars, more galaxies, and more universes. Some of these universes might be larger and older, while others could be smaller and younger. They are distributed in a larger spacetime, expanding rapidly and irreversibly, with the spacetime containing them expanding even faster, causing them to drift apart. This ensures that no two universes collide. This is the concept of the multiverse. If the universe adheres to the principles of quantum physics, the existence of a multiverse is almost an inevitable outcome. Despite various theoretical perspectives, there is undeniable order in our universe. The speed of light remains constant, and the thermodynamic laws apply consistently across every corner of the cosmos. From the smallest particles to the largest structures, the rules hold true. The ratio between strong nuclear force and electromagnetic force is finely tuned, allowing for the formation of stars and galaxies. The dials controlling these parameters seem meticulously adjusted, as if the universe, to some extent, is finely tuned for our existence. Although we haven't yet found a theory that ties everything in the universe together, and the workings of the cosmos surpass our cognitive and comprehending capabilities, we do know that we are a part of this vast and intricate universe that eludes complete understanding. So, the next time you gaze at the stars, take a moment to appreciate the perfection of the universe. Remind yourself that we live in an incredible, mysterious, and beautiful world.